What if I told you the universe we call home, with all its galaxies, stars, and mysteries, might not be the only one out there? And what if, in the vast expanse of existence, our universe once smashed into another, like two titans clashing in the dark? This isn't just science fiction. It's a real scientific possibility that could rewrite everything we think we know about reality. Picture this: the fabric of space and time rippling like a pond after a stone's toss, cosmic echoes of a collision so colossal, it might have left scars we're only now learning to see. For centuries, we've gazed at the night sky, wondering if we're alone. But what if the question isn't just about life? What if it's about the very nature of existence itself? Imagine two universes, each with its own laws of physics, its own history, its own destiny, until one fateful moment when they crossed paths, the aftermath. A cosmic fingerprint hidden in the oldest light in the universe, strange anomalies in the way galaxies move, or even ripples in the very structure of reality. Scientists are hunting for these clues right now, piecing together a puzzle that could change our understanding of everything. This is the mystery we're diving into today, the mind-bending idea that our universe might have tangled with another, leaving behind evidence we're just beginning to decode. From cutting-edge simulations to bizarre gravitational waves, from theoretical physics to the edges of observable space, we're going to explore the theories, the evidence, and the breathtaking implications of a multiverse collision. So buckle up. By the end of this journey, you might never look at the night sky the same way again, because if our universe isn't alone, what else is out there? To understand how our universe could collide with another, we first need to grasp the wild idea at the heart of it all: the multiverse. Think of reality not as a single, solitary universe, but as an endless cosmic tapestry, woven with countless other universes, each with its own unique rules, histories, and even versions of you. This isn't just wild speculation. Some of the brightest minds in physics argue that multiple universes could exist, separated by dimensions we can't perceive or scattered like bubbles in an infinite foam. One of the most famous interpretations is the many worlds theory, born from quantum mechanics. Every time a decision is made, whether it's an electron spinning left or right, or you choosing coffee over tea, this theory suggests reality splits, creating branching timelines where every possible outcome plays out. It's like a cosmic choose-your-own-adventure where every path is real, just in a different universe. Then there's the bubble universe idea, where new universes constantly inflate like bubbles in an endless cosmic ocean, each with its own physics. Some might have stronger gravity, others might collapse instantly, and a rare few like ours could have just the right conditions for life. But if these universes exist, could they ever bump into each other? Some theories say absolutely. Picture two soap bubbles floating in the air. If they touch, their surfaces ripple, merge, or even pop. Now imagine that on a cosmic scale. A collision between universes might leave behind wrinkles in space-time, strange patterns in the cosmic microwave background, or even bizarre gravitational effects we haven't yet explained. Scientists are scouring the skies for these anomalies, hunting for the fingerprints of a universe beyond our own. The implications are staggering. If another universe once crashed into ours, it could mean our reality is just one fragment of something far grander. It could rewrite the laws of physics, redefine our place in existence, and force us to ask, if universes collide, what else is possible? If we want proof that our universe might not be alone, we don't have to look far. Some of the most compelling clues are already hiding in plain sight. Take the cosmic microwave background, for example. This faint afterglow from the Big Bang blankets the entire sky like a fossilized snapshot of the universe's infancy. But when scientists examined it closely, they found something bizarre. A strange, unexplained cold spot stretching across billions of light years. One possible explanation: The gravitational tug of a neighboring universe warping space-time like a fingerprint pressed against the fabric of our own. It's as if we're seeing the shadow of something vast lurking just beyond the edges of what we can perceive. Then there's the mystery of dark flow. Astronomers have observed entire clusters of galaxies moving in the same direction at staggering speeds, as if some invisible force is pulling them. The unsettling part, there shouldn't be anything massive enough in our known universe to cause such a motion. Could this be the gravitational echo of another universe tugging at ours from the outside? It sounds like something from a sci-fi novel, but the math doesn't lie. These anomalies fit eerily well with theories of colliding or neighboring universes. Quantum mechanics adds another layer of strangeness. Particles at the smallest scales behave in ways that defy logic, appearing to influence each other instantaneously across vast distances, a phenomenon Einstein famously called spooky action at a distance. Some physicists argue this could be evidence of parallel realities bleeding into one another. Imagine two universes so close their particles are entangled, dancing in sync despite the divide. It's a radical idea, but in a multiverse, the rules we take for granted might not apply. Even gravity itself could be a clue. In our universe, it's shockingly weak compared to other forces, so weak that a tiny magnet can overpower Earth's entire gravitational pull. Why? One theory suggests gravity might be leaking into other dimensions, thinning out as it spreads across multiple universes. It's like trying to fill a bathtub with a hose that's spraying water in all directions. You'd never get the full force in one place. The hunt for parallel universes isn't just about cosmic curiosities. It's a revolution in how we see reality. Every anomaly, every unexplained ripple could be a breadcrumb leading us to the next great discovery. And if we're right, the multiverse just got a whole lot bigger. The notion that entire universes could collide isn't just a fantastical thought experiment. It's a serious scientific hypothesis with roots in some of the most advanced physics we have. Take string theory, for example. This ambitious framework attempts to unify all the forces of nature by suggesting that the fundamental building blocks of reality aren't particles but tiny, vibrating strings. And within string theory lies a particularly mind-bending idea called brane cosmology. Picture our universe as a three-dimensional membrane, or brane, floating in a higher dimensional space. Now imagine another brane, another universe, drifting alongside ours in this unseen expanse. If these branes were to move or ripple, they could slam into each other like sheets of paper swaying in a breeze, except instead of a rustling sound, you'd get a cataclysm that reshapes reality itself. This isn't just abstract math. Some physicists argue that such a collision could have even triggered our own Big Bang. The idea is that when two branes collide, the energy released might be so immense it spawns an entirely new universe. Think of it like striking two rocks together to create a spark, except the spark is an explosion of space, time, and matter. It's a radical twist on the traditional Big Bang story, one where our universe isn't born from nothing but from the aftermath of a cosmic traffic accident in a higher dimension. But how would we ever detect such an event? If universes collided, the impact might leave behind gravitational waves, ripples in space-time so powerful they'd still echo billions of years later. Advanced detectors like LIGO are already hunting for these waves, and while most signals come from black holes or neutron stars, there's always the chance something far stranger could appear in the data. Another clue could be hidden in the distribution of galaxies. A universe-shattering collision might have sent shockwaves through the early cosmos, nudging matter into unusual patterns we're only now beginning to map. Of course, not all collisions would be apocalyptic. Some models suggest universes might brush past each other gently, leaving subtle distortions in their wake. Imagine two soap bubbles barely touching their surfaces might warp slightly before drifting apart. In cosmic terms, that could mean faint temperature variations in the cosmic microwave background or mysterious voids in the large-scale structure of the universe. These fingerprints would be incredibly subtle, but as our telescopes and simulations grow more sophisticated, we might finally spot them. What's fascinating is how these ideas blur the line between science and philosophy. If universes can collide, could they also exchange matter or even life? Could physical laws bleed from one into another, creating regions where gravity behaves oddly or time flows backward? The implications are as thrilling as they are unsettling. We're not just talking about distant, untouchable realms, we're grappling with the possibility that our universe is part of a dynamic, ever-changing multiverse where the rules we know are just one variation in an infinite symphony of possibilities. This is the frontier of cosmology, where the boldest ideas challenge everything we assume about existence. And while we don't have definitive proof yet, the very fact that brilliant minds take these theories seriously tells us something profound. The universe or multiverse is far stranger and more wondrous than we ever imagined. One of the most tantalizing clues in the search for a multiverse collision lies in the cosmic microwave background, the faint whisper of light left over from the birth of our universe. Stretching across the entire sky, this ancient glow is like a cosmic fingerprint, carrying secrets from a time when the universe was just a searing hot soup of particles. But when scientists mapped it with extreme precision, they stumbled on something bizarre: a mysterious cold spot, a patch of sky where the temperature dips unexpectedly, as if the universe itself has a bruise. This cold spot isn't just a tiny anomaly. It spans nearly 1 billion light-years, a vast region of space where the rules seem slightly off. At first, astronomers thought it might be a statistical fluke or an error in the data. But the more they studied it, the stranger it became. The cold spot persists, defying conventional explanations. One radical possibility: it could be the scar of a collision with another universe. Think of it like two giant bubbles floating in a bath. When they touch, the point of contact leaves a distortion, a dent in the surface. If our universe brushed against another, the energy of that impact might have created a void, a cosmic dent that cooled the surrounding space in a way we can still detect today. There's another eerie detail. The cold spot isn't just cold, it's surrounded by a ring of slightly warmer radiation, like ripples around a stone dropped in a pond. This pattern matches what some theoretical models predict for a multiverse collision, where the gravitational tug of another universe warps space-time, leaving behind a thermal fingerprint. Skeptics argue it could be caused by a supervoid, an enormous empty region of space where matter is unusually sparse. But even then, the scale of the cold spot is so extreme that it challenges our understanding of how such voids form. The implications are staggering. If this cold spot really is evidence of a multiverse collision, it would mean we're not just mapping our universe, we're glimpsing beyond it. Imagine standing in a room and seeing a shadow on the wall, realizing it's cast by something outside, something you can't directly see. That's the tantalizing possibility here. The cold spot might be our first peek into a reality beyond our own, a cosmic handshake from another universe. Of course, science demands more than just intriguing maybes. Researchers are refining telescopes and simulations to test this idea further. Future observations could reveal more about the cold spot structure, searching for telltale patterns that rule out mundane explanations. Until then, this enigmatic patch of sky remains one of the most compelling mysteries in cosmology, a silent, chilling hint that our universe might not be as alone as we once thought. Picture our cosmos not as a lone, static entity, but as a frothing sea of universes, each one a bubble inflating endlessly, sprouting from the quantum foam of existence. This is the heart of inflationary theory, which suggests that the Big Bang wasn't a one-time event but part of an endless cycle where new universes constantly blink into being. Imagine a pot of water boiling violently, with bubbles forming, expanding, and sometimes merging. Now replace the water with the fabric of space-time itself, and those bubbles with entire universes, each birthing its own stars, galaxies, and perhaps even life. In this cosmic bubble bath, collisions aren't just possible, they're inevitable. When two bubble universes expand too close to one another, their boundaries can touch, sending shockwaves rippling through both realities. The energy of such an impact would be unimaginable, like two galaxies colliding, but on a scale so vast it defies comprehension. Some models suggest these collisions could leave behind cosmic scars, wrinkles in space-time or bizarre distortions in the distribution of matter. Others propose that when bubbles merge, their physical laws might temporarily clash, creating regions where gravity behaves erratically or light travels at different speeds. One of the most striking implications comes from eternal inflation, a theory where the process of universe creation never stops. In this scenario, our universe is just one bubble in an infinite multiverse, forever growing alongside countless others. Occasionally, these bubbles might brush against each other, not with a cataclysmic crash but with a subtle nudge enough to leave faint imprints in the cosmic microwave background or alter the way galaxies cluster together. The wildest part, if bubble universes can collide, they might also exchange material. Imagine a universe where the laws of physics are slightly different, maybe gravity is stronger or time flows backward. If it bumped into ours, could fragments of that reality seep into ours? Could there be patches of space where the rules we know don't apply? It's a dizzying thought, but one that pushes the boundaries of what we consider possible. Scientists are already hunting for signs of these collisions. Telescopes scan the sky for anomalous temperature fluctuations, while advanced simulations recreate how bubble universes might interact. Each strange pattern in the data, each unexplained void in the cosmos, could be a breadcrumb leading us closer to proof that we're not alone in the multiverse. And if we ever find definitive evidence, it would mean our universe is just one note in an infinite cosmic symphony, a humbling, exhilarating revelation that redefines our place in existence. String theory takes the already mind-bending idea of colliding universes and cranks it up to 11. At its core, this framework suggests that the fundamental particles we know, electrons, quarks, photons, aren't dots at all, but tiny, vibrating strings. And just like a guitar string can play different notes, these cosmic strings vibrate in unique ways to create every particle and force in existence. But here's where it gets wild. String theory requires extra dimensions beyond the 3 we experience daily. Not just 4 or 5, but 10 or even 11 dimensions, all curled up or hidden from our perception. In this higher dimensional landscape, our universe might not be floating alone. Imagine it as a 3-dimensional membrane or brane stretching through these unseen dimensions like a sheet of paper suspended in midair. Now picture another brane, another universe, drifting nearby in this cosmic void. According to brane cosmology, these membranes could move, ripple, or even slam into each other with unimaginable force. The collision wouldn't be like two planets crashing. It'd be more like two entire realities brushing against one another in a space we can't even see. The aftermath of such an event could rewrite physics itself. Some theorists propose that the Big Bang wasn't a singular explosion from nothing, but the shockwave of two branes colliding. Think of it like cymbals clashing in an orchestra. The reverberations would unleash enough energy to birth an entirely new universe. This ekpyrotic model suggests our cosmos began not with a bang, but with a cosmic fender bender in a higher dimension. And if that's true, the echoes of that collision might still linger. But how would we detect something like that? For starters, a brane collision could send gravitational tsunamis rippling through space-time. These wouldn't be the run-of-the-mill waves from black hole mergers. They'd be primordial, universe-spanning distortions with unique signatures. Next-gen detectors might one day pick up these whispers from beyond our brain. There's also the possibility of imprints left in the cosmic microwave background. Just as a pebble dropped in a pond creates concentric ripples, a brane collision could have left faint thermal patterns in the afterglow of creation patterns we're only now learning to decode. What if these collisions aren't just ancient history? In an infinite multiverse, branes might be bumping into each other all the time. Some models suggest our universe could even be sandwiched between others, like pages in a book with gravity leaking between them. This could explain why gravity feels so weak compared to other forces. It's not fading away. It's spreading out across dimensions we can't access. The implications are dizzying. If branes can collide, could they also merge? Could pockets of our universe carry remnants of another's physics, places where matter behaves strangely or time flows differently? String theory doesn't just open the door to other universes. It suggests we might be living in a cosmic neighborhood where reality is far more fluid than we ever imagined. Every unexplained anomaly, every gravitational hiccup could be a clue that we're not just studying the universe, we're eavesdropping on the multiverse. Simulating what happens when universes collide isn't just about wild speculation, it's a scientific frontier where supercomputers act as cosmic time machines, crunching numbers so vast they'd take human minds millennia to process. These digital experiments recreate scenarios straight out of multiverse theory, letting researchers watch entire universes smash together in hyperspeed. One of the most groundbreaking projects comes from Durham University, where astrophysicists programmed a supercomputer to simulate brane collisions, those higher dimensional crashes predicted by string theory. The results were staggering. When two branes collided in the simulation, they didn't just bounce off each other like billiard balls. Instead, the energy of the impact triggered explosive bursts of matter and radiation, eerily resembling the conditions of our own Big Bang. But how do you even build a model of something as unfathomable as a universe collision? Scientists start with equations, mathematical frameworks describing how gravity, quantum fields, and spacetime behave under extreme conditions. Then they feed these equations into supercomputers, which divide the problem into billions of tiny calculations. Imagine trying to predict how a drop of ink spreads in a swimming pool by tracking every single molecule. Now scale that up to galactic proportions, factoring in dark energy, higher dimensions, and the bizarre physics of other universes. The simulations don't just show collisions, they reveal the aftermath, mapping how matter clumps into galaxies or how spacetime ripples with gravitational echoes. Some simulations focus on bubble universes, those cosmic pockets inflating eternally in the multiverse. When these bubbles collide, they don't always annihilate each other. Instead, they might create bizarre defects in spacetime cosmic strings or domain walls where the laws of physics change abruptly. Picture two soap bubbles merging. The spot where they touch forms a ring, a boundary between two distinct surfaces. In a universe collision, that boundary could be a place where gravity flips direction or time runs sideways. Supercomputers help scientists spot these anomalies by generating ultra-detailed visualizations, like cosmic weather maps for multiverse storms. The real power of these simulations lies in their predictive power. If a model says universe collisions should leave certain fingerprints, like specific patterns in the cosmic microwave background or unusual gravitational wave signatures, astronomers know exactly what to hunt for in real data. It's like having a cheat sheet for the cosmos. Already, teams are comparing simulation results with telescope observations, searching for matches that could confirm we're not alone in the multiverse. Every strange cold spot or inexplicable galaxy motion could be the key, and supercomputers are helping us decipher the clues. The traditional story of the Big Bang paints it as the ultimate beginning, a singular explosion where space, time, and matter burst into existence from nothing. But what if that's not the full picture? What if the Big Bang wasn't a birth from void, but the thunderous aftermath of something even grander, a collision between universes? This radical idea turns cosmology on its head, suggesting our universe didn't emerge alone but was forged in the chaos of a multiverse crash. Imagine two enormous sheets of reality floating in a higher dimensional space we can't perceive. These aren't just physical objects, they're entire universes, each with their own laws and history. Now picture them drifting closer until they touch. The energy released wouldn't just be a spark, it'd be a conflagration, a fireball so intense it could ignite an entire new cosmos. This is the essence of the ekpyrotic model, a theory proposing that our Big Bang was actually the moment two branes, those multidimensional membranes from string theory, slammed together in a higher dimensional void. The evidence for this audacious idea isn't purely theoretical. When scientists examine the cosmic microwave background, the afterglow of the Big Bang, they find patterns that don't quite fit the standard model. Tiny temperature fluctuations, unexpected voids, and strange alignments in the fabric of space could all be echoes of a pre-Big Bang event. Some researchers argue these anomalies look less like the remnants of a spontaneous explosion and more like the scars of a collision, as if the universe is still shuddering from the impact. But how could a collision create a universe? Think of it like clapping your hands. The energy of your palms striking doesn't just vanish, it transforms into sound waves, heat, and vibration. In the same way, when branes collide, their energy doesn't disappear. It transmutes into the raw materials of a new reality, particles, radiation, even the very fabric of space-time itself. This process might not just happen once. In an infinite multiverse, countless branes could be ricocheting off one another, each collision birthing a fresh universe with its own unique properties. Critics argue that without direct observation of these higher dimensions, the idea remains speculative. But supporters counter that the same was once said about black holes and gravitational waves, a phenomenon now confirmed by cutting-edge science. The hunt for proof is already underway. Advanced telescopes scour the cosmos for gravitational wave signatures that don't match known astrophysical events. Particle accelerators probe energies so high they might reveal traces of extra dimensions. Even the subtle spin of distant galaxies could hold clues, their motions hinting at gravitational tugs from realities beyond our own. If this theory holds, it rewrites not just the origin of our universe, but its future. A collision-born cosmos might face another impact down the line, a cyclical universe where beginnings and endings are just phases in an eternal dance of creation. The heat death or big crunch scenarios fade away, replaced by the dizzying possibility that universes live, collide, and rebirth in an endless chain. It's a vision both humbling and exhilarating, reminding us that even the mightiest events in our reality might just be footnotes in a far vaster story. Among the cosmic mysteries challenging our understanding of the universe, few are as perplexing as dark flow, the eerie phenomenon where entire clusters of galaxies seem to be pulled in the same direction, as if caught in a silent river flowing through the void. This isn't just random motion. These galaxies are racing at speeds exceeding 2 million miles per hour toward a point in space with no apparent explanation, like leaves swept along by some invisible current. The unsettling part, there's nothing in our observable universe massive enough to exert such a gravitational tug. So what's dragging them? One startling possibility is that the pull isn't coming from inside our universe at all. Imagine standing in a room and feeling a draft, not from an open window, but from a hidden doorway leading somewhere unseen. Dark flow could be the gravitational equivalent of that draft, a sign that something vast, perhaps another universe, lies beyond the boundaries of our cosmic map, its gravity warping the fabric of our reality. This idea gained traction when astronomers studying galaxy clusters in the cosmic microwave background noticed their motion defied all expectations. The clusters weren't just drifting randomly with the expansion of space, they were marching in unison toward a distant, unseen attractor. Critics argue this motion might be an illusion, a statistical fluke, or an artifact of incomplete data, but the evidence is mounting. When researchers traced the flow, they found it extends billions of light years, far beyond the reach of any known supercluster or dark matter structure. Even more intriguing, the direction of the flow aligns with anomalies in the cosmic microwave background, those same temperature variations some theorize could mark a multiverse collision. It's as if two pieces of a puzzle, separated by time and space, are whispering the same secret. The implications are profound. If dark flow is real, it suggests our universe isn't a closed system, it's interacting with something external. Some models propose this could be a remnant of the pre-Big Bang era, a time when our universe was entangled with others in a higher dimensional space. Others speculate it might be evidence of a mother universe that birthed ours, its gravity still tugging at us like an umbilical cord never fully severed. Of course, extraordinary claims demand extraordinary proof. Future telescopes like the European Space Agency's Euclid mission aim to map dark flow with unprecedented precision, searching for patterns that could rule out conventional explanations. Until then, dark flow remains one of cosmology's most tantalizing enigmas, a ghostly current in the cosmic ocean, hinting that we're not just floating alone, but adrift in something far greater. Quantum entanglement is one of the most bizarre phenomena in physics. Particles separated by vast distances can instantly influence each other's states, as if they're dancing to some hidden rhythm. Einstein famously dismissed it as spooky action at a distance, but what if the spookiness runs even deeper? Some physicists now speculate that entanglement might not just connect particles within our universe, it could be a cosmic thread tying us to parallel realities. Picture two entangled particles like a pair of dice rolled in different galaxies. No matter how far apart they are, if one lands on 6, the other instantly shows a 6 too. This happens faster than light could travel between them, violating everything we know about locality and causality. The standard explanation is that the particles share a quantum state, but an even wilder idea is that their connection isn't through our universe at all, it's through another. Think of it like two rooms separated by a wall. If you knock on one side, the sound travels through the wall to the other. In this case, the wall might be a higher dimensional space where universes brush against each other, letting particles whisper across the divide. This idea stems from the many worlds interpretation of quantum mechanics, where every possible outcome spawns a new universe. When particles entangle, their states might be linked because they're mirroring counterparts in alternate realities. Imagine two versions of you in parallel worlds, each holding one of the dice. When your double rolls a 6, you roll 1 too, not because of magic, but because your realities are still subtly connected. It's as if the multiverse leaves tiny doors ajar between its branches, and entanglement is the faint breeze slipping through. The math behind this isn't just speculative. Some models in string theory suggest that entangled particles could be in points of higher dimensional wormholes, bridges stitching together separate universes. These wormholes wouldn't be tunnels you could travel through, they'd be microscopic, fleeting, and governed by quantum weirdness. But their existence could explain why entanglement defies classical physics. If particles are linked through shortcuts in spacetime that bypass our universe entirely, their instant connection starts to make sense. Experiments are already probing these radical possibilities. Quantum physicists are testing whether entanglement leaves traces in the fabric of spacetime, like minuscule gravitational anomalies. Others are searching for patterns in particle behavior that might hint at interference from parallel realities. It's a long shot, but if proven, it would mean entanglement isn't just a quirk of our universe, it's a lifeline to others. The implications are staggering. If quantum links span the multiverse, could information or even energy leak between them? Are there places in our universe where the boundaries are thin, creating zones of altered physics? And if particles can communicate across realities, what else might be slipping through the cracks? Every entangled pair might be more than a lab curiosity. It could be a window into the infinite. Black holes have long been the ultimate cosmic enigmas, regions where gravity is so intense, not even light can escape. But what if these bizarre objects aren't just cosmic vacuum cleaners? What if they're relics of ancient universe collisions or even secret passageways to other realities? The idea might sound like pure science fiction, but some of the most respected theories in physics suggest black holes could be far more than meets the eye. Take the concept of wormholes, for example. Einstein's equations of general relativity allow for the existence of these hypothetical tunnels through space-time, shortcuts connecting distant points or even different universes. While we've never observed a wormhole directly, some scientists propose that certain black holes might contain them hidden beyond their event horizons. Picture a black hole not as a dead end but as a cosmic turnstile. Matter gets sucked in, crushed to infinite density, and then where does it go? One possibility is that it emerges somewhere else entirely, perhaps in another universe altogether. But how could this tie into multiverse collisions? Imagine two universes brushing past each other like passing ships in the night. The gravitational upheaval of such an encounter might warp spacetime so violently that it creates ultra-dense knots, black holes with bizarre properties. Some theories even suggest these black holes could retain a faint memory of the collision, their internal structure reflecting the physics of the other universe. It's like finding a piece of driftwood on a beach with markings from a distant shore, an artifact proving there's something beyond the horizon. The most mind-bending version of this idea comes from loop quantum gravity, a framework that reimagines spacetime as a woven fabric of tiny, indivisible loops. In this model, black holes might not end in singularities, those infinitely dense points at their cores, but instead rebound, spewing their contents into a new region of space. Think of it like a cosmic bounce. A collapsing star doesn't vanish into oblivion but springs back, potentially birthing a new universe on the other side. If that's true, our own Big Bang could have been the other side of a black hole collapse in another reality. Could we ever find evidence for this? Some physicists speculate that certain black holes might emit subtle signatures, unusual gravitational wave patterns, or exotic particle emissions that betray their origins as multiverse collision remnants. Others suggest that microscopic black holes, if they exist, might behave in ways that defy our universe's physics, hinting at their connection to another cosmos. Then there's the eerie case of white holes, the hypothetical opposites of black holes, where matter and energy erupt outward instead of vanishing inward. While no white hole has ever been observed, they emerge naturally in some equations as potential exits for black hole tunnels. If they do exist, they might be the glowing exit wounds of universe collisions, places where the debris of one reality spills into another. Of course, the ultimate question isn't just whether black holes lead elsewhere, but what happens if you dive into one. Hollywood loves the idea of astronauts surviving the trip, but reality would be far less forgiving. The tidal forces near a black hole's event horizon would stretch and compress anything, or anyone, into a stream of atoms long before reaching the other side. Yet mathematically, the possibility remains. Black holes could be one-way doors to places beyond our imagination, cosmic souvenirs from a time when universes touched. The search for answers is already underway. Telescopes like the Event Horizon Telescope, which captured the first image of a black hole's shadow, are pushing the limits of what we can observe. Meanwhile, quantum gravity researchers are refining models to predict how black holes might behave if they truly are portals. Every new discovery peels back another layer of the mystery, revealing just how little we truly understand about these gravitational monsters and how much they might be hiding. What if the birth and death of our universe isn't a one-time event but part of an infinite loop, a cosmic heartbeat where universes collide, die, and are reborn in an endless cycle? This is the spine-tingling premise of cyclic cosmology, a theory that rewrites the story of everything we know. Instead of a single Big Bang followed by an eventual cold, dark fade into nothingness, this model suggests universes rise and fall like waves in an ocean, each collision igniting the next. Picture two colossal sheets of reality drifting toward each other in higher dimensional space, meeting with enough force to obliterate everything only for that destruction to seed a new beginning. The cyclic model isn't just poetic, it's grounded in serious physics, stemming from string theory and brane cosmology. It proposes that our universe exists on a three-dimensional membrane, or brane, floating near others in a hidden dimension. Every few trillion years, these branes could draw close enough to collide, releasing energy so immense it triggers a new Big Bang. The old universe's matter and energy are recycled, its galaxies and stars vaporized into a seething plasma, ready to form anew. It's the ultimate cosmic reboot, where destruction and creation are two sides of the same coin. What's fascinating is how neatly this solves some of cosmology's biggest puzzles. Take the arrow of time, for instance. In our universe, time flows inexorably forward, eggs crack but never uncrack, stars burn out but never reignite. But in a cyclic cosmos, time's arrow might reset with each collision, offering a fresh direction with every rebirth. Then there's dark energy, the mysterious force accelerating our universe's expansion. Cyclic models suggest it's not a constant but a phase, a push that prepares the cosmos for the next collision by thinning out matter and smoothing space-time, like a canvas being wiped clean for a new painting. Evidence for this audacious idea might already be hiding in plain sight. If past universe collisions left imprints in the cosmic microwave background, those faint temperature variations we've detected, they could resemble subtle, concentric ripples radiating across the sky. Some researchers argue that certain anomalies, like the infamous cold spot, fit this pattern eerily well. Others hunt for gravitational wave signatures with telltale frequencies, traces of ancient brane collisions echoing through space-time like a gong struck billions of years ago. But the most mind-bending implication, if the cycle is truly eternal, our universe isn't the first and won't be the last. Countless versions of reality may have existed before us, each with its own laws, its own stories, its own civilizations gazing up at their night skies asking the same questions. And if the cycle continues, our fate isn't oblivion, it's transformation. Every black hole, every dying star, every atom in our bodies might one day fuel a new cosmos, another chapter in an infinite saga of collisions and rebirths. The universe isn't just stranger than we imagine. It's stranger than we can imagine, a cosmic phoenix rising again and again from its own ashes. The idea that our universe seems perfectly tailored for life has puzzled scientists for decades. Every fundamental force, every constant in nature, appears precisely calibrated to allow stars, planets, and ultimately, conscious beings like us to exist. Tweak gravity just slightly stronger and stars would burn out too quickly. Adjust the strength of the nuclear forces and atoms might never form. It's as if the cosmos was designed with life in mind, a phenomenon known as the anthropic principle. But what if this delicate balance isn't the result of design or sheer luck? What if it's the product of countless universes colliding, with ours simply being the one where the dice rolled in favor of life? Here's where the multiverse crashes into the anthropic principle. If an infinite number of universes exist, each with its own random set of physical laws, then statistically, some of them will inevitably have the right conditions for life. Most might be barren, with gravity too weak to form galaxies or electromagnetism too strong to allow stable atoms. But in a sea of failed universes, a rare few, like ours, would hit the cosmic jackpot. Now imagine those universes aren't just floating in isolation. If they collide, the very act of smashing together could reshape their laws, scrambling the constants of physics like dice in a cup. Our universe might be the result of such a collision, a cosmic reset that left it with just the right parameters for complexity to emerge. Some theories take this even further. In brane cosmology, when two universes collide, the energy released doesn't just create a new universe, it could also select for stable, life-friendly physics. Think of it like shaking a box of sand. At first, the grains are disordered, but over time, they settle into the most stable arrangement. Similarly, universe collisions might act as a filter, weeding out unstable configurations and leaving behind those capable of sustaining structure. This could explain why our universe seems fine-tuned, not because it was designed that way, but because chaotic, high-energy collisions tend to produce order over time. There's another twist. If multiple universes have collided throughout cosmic history, their interactions might create localized pockets where physics varies slightly. Picture a vast ocean with currents flowing in different directions. Our observable universe could be one calm eddy in a turbulent multiverse, a region where the conditions just happen to align for life. Elsewhere, physics might be wildly different, but we wouldn't know because we can only exist where the numbers add up right. This selection effect means we're not observing a special universe, we're observing the only kind of universe where observation is possible. The implications are profound. If collisions fine-tune universes for life, then the multiverse isn't just a random assortment of realities, it's a dynamic ecosystem where universes interact, evolve, and occasionally produce environments capable of asking why they exist. It turns the mystery of fine-tuning from a philosophical question into a physical process, something we might one day detect in the cosmic microwave background or hidden gravitational wave signals. Critics argue this is just kicking the can down the road, replacing one mystery with another, but supporters counter that it's no different from how science has always progressed. We once thought Earth was the center of the universe, then the solar system, then the galaxy. Each time, the answer was simpler: we're not special, just part of something bigger. The anthropic principle, shaped by collisions, suggests the same might be true of reality itself. Our universe isn't fine-tuned because it's unique, it's fine-tuned because it survived. While scientists crunch equations and scan the cosmos for evidence of universe collisions, storytellers have been imagining these cataclysmic encounters for decades, often with spectacular results. Take Marvel Comics incursions, for example, where entire universes crash into one another like celestial freight trains, threatening to annihilate everything in their path. In this gripping storyline, entire Earths from different realities collide, forcing heroes to make impossible choices, sacrificing one world to save another. It's not just explosive action, it's a thought experiment about what survival really means in a multiverse where existence is fragile. The concept isn't limited to comic books. Rick and Morty turned universe hopping into a dark comedy, showcasing alternate realities where collisions aren't just possible, they're routine. One infamous episode sees the protagonists abandoning their own doomed dimension after a dimensional merge, only to bury their own corpses in a nearly identical world. The show's absurdity masks a chilling truth. In an infinite multiverse, destruction and rebirth might be as mundane as changing clothes. Then there's Doctor Strange in the multiverse of madness, where the fabric between realities tears open, unleashing chaos. The film visualizes universe collisions as apocalyptic storms, with matter and physics warping unpredictably. Buildings fold into themselves, gravity reverses midair, and characters are shredded into mere particles, all because the boundaries between worlds weren't just crossed but shattered. Hollywood's take might be exaggerated, but it echoes real scientific anxieties about what might happen if branes or bubble universes ever clashed. Literature dives even deeper. In the Long Earth series by Terry Pratchett and Stephen Baxter, humanity discovers infinite parallel Earths, each slightly different from our own. The story explores not just collisions, but the psychological toll of knowing your universe isn't unique. Meanwhile, Dark Matter by Blake Crouch imagines a machine that lets users leap between realities until the walls between them start collapsing, blending timelines into a surreal, unstable nightmare. What's fascinating is how these fictional portrayals mirror real theories. When Everything Everywhere All at Once depicts universes as branching fractals where every choice spawns a new reality, it's riffing on the many worlds interpretation of quantum physics. When fringe shows alternate dimensions bleeding into each other, creating hybrid zones with scrambled laws, it's not far from brane cosmology's predictions. Even Interstellar, with its higher dimensional tesseract, hints at how colliding universes might warp time and space beyond recognition. But pop culture doesn't just borrow from science, it pushes the boundaries of imagination. While physicists debate cold spots and gravitational anomalies, storytellers ask the human questions. What would it feel like to witness your universe colliding with another? Would we fight to save our reality or embrace the chaos? These narratives remind us that the multiverse isn't just a cosmic puzzle. It's a mirror reflecting our deepest fears and fascinations about existence itself. And sometimes the wildest fiction gets us closer to the truth than we realize. Not everyone is convinced that our universe has ever collided with another. Some scientists argue that the very idea of a multiverse collision is more philosophy than physics, an untestable hypothesis dressed up in mathematical equations. After all, if other universes exist beyond our observable horizon, how could we ever gather evidence to prove they've interacted with ours? This skepticism isn't just nitpicking, it cuts to the heart of what makes science science. A theory isn't truly scientific unless it can be tested, falsified, and verified through observation. And right now, critics say multiverse collisions fall short. One major sticking point is the cosmic microwave background's mysterious cold spot. While some researchers see it as a potential collision scar, others argue it could just as easily be a statistical fluke, a cosmic roll of the dice in an infinite sky. The universe is vast, and improbable patterns are bound to emerge somewhere. Without a smoking gun, like a distinct gravitational wave signature or repeatable patterns across multiple observations, the cold spot remains tantalizing but inconclusive. Even if it were caused by a collision, how would we rule out all other possible explanations? The burden of proof, skeptics insist, is staggering. Then there's the problem of higher dimensions. String theory and brane cosmology rely heavily on dimensions we can't see or measure. If these extra dimensions exist, they're presumably curled up at scales so tiny, no experiment could ever detect them directly. Critics compare this to explaining a missing sock by inventing an invisible sock-stealing elf. It might solve the puzzle, but without a way to observe the elf, the explanation isn't scientific. Nobel laureate Richard Feynman once quipped, "If it disagrees with experiment, it's wrong." In that simple statement is the key to science. By that standard, multiverse collisions are skating on thin ice. Even the math behind these theories has drawn fire. Some physicists point out that string theory, for all its elegance, hasn't yet produced a single testable prediction unique to it. The same goes for brane collisions. While the equations might allow for such events, they don't require them. In science, a theory that can explain anything often ends up explaining nothing. Without clear boundaries, predictions that, if proven wrong, would sink the theory at risks becoming a just-so story, flexible enough to fit any observation after the fact. But perhaps the sharpest criticism comes from Occam's razor, the principle that the simplest explanation is usually the right one. Invoking an infinite multiverse to explain quirks in our universe might seem like overkill. Why conjure countless unseen realities when the anomalies we've found, like dark flow or quantum entanglement, might just be gaps in our current understanding of this universe? After all, history is littered with mysteries once attributed to the supernatural or the unknowable, only to yield to mundane, natural explanations later. That said, defenders of collision theory counter that skepticism is healthy, but so is daring to explore the unknown. Every revolutionary idea in science, from continental drift to dark matter, faced initial dismissal. The key, they argue, is to refine rather than reject. New telescopes, more sensitive gravitational wave detectors, and advanced simulations could one day turn today's speculation into tomorrow's textbook fact. Until then, the debate itself drives progress, forcing both sides to sharpen their arguments and dig deeper into the cosmos' secrets. The universe doesn't owe us easy answers, but that's what makes the hunt so thrilling. The cold spot in the cosmic microwave background might not necessarily be a multiverse collisions calling card. It could also be the work of cosmic defects, bizarre structures left over from the universe's earliest moments. Imagine spacetime not as a smooth fabric but as a frozen lake with cracks and fissures formed during its formation. These imperfections, known as topological defects, could be the culprits behind some of the universe's strangest anomalies, including that eerie cold patch in the sky. One leading candidate is the cosmic texture, a theoretical kink in spacetime that formed when the fundamental forces of nature froze into their current state during the universe's rapid cooling after the Big Bang. Picture a knitted sweater with a snagged thread, the surrounding fabric puckers creating a distortion. Similarly, a cosmic texture would warp spacetime around it, subtly altering the path of light and leaving behind temperature variations in the cosmic microwave background. If such a texture exists near the cold spot, it could explain the anomaly without invoking other universes. Then there are domain walls, enormous, sheet-like structures marking boundaries where the laws of physics change abruptly. These walls would form if certain quantum fields settled into different states in different regions of the early universe, like a patchwork quilt stitched together from mismatched fabric. A domain wall passing through our cosmic neighborhood could bend light, distort gravitational fields, and leave behind cold spots or other irregularities. While no direct evidence of domain walls exists yet, their shadows might lurk in the cosmic microwave background's faintest patterns. Another possibility involves cosmic strings, infinitely thin, unimaginably dense filaments of energy stretched across the universe like cracks in a frozen pond. These relics of the early cosmos would carry tremendous mass, warping spacetime around them as they move. If a cosmic string passed through our line of sight, it could split the light from distant galaxies, creating double images or temperature dips in the cosmic microwave background. Some researchers argue that the cold spot's shape and size could match the signature of such a string, though pinpointing one remains elusive. The challenge with these cosmic defect theories is that they require incredibly precise conditions to produce the anomalies we observe. A texture or string would need to be positioned just right, and its effects fine-tuned to match the cold spot's exact profile. Skeptics point out that defects should also produce other detectable signals, like distinctive gravitational lensing patterns or ripples in galaxy distributions, yet so far, none have been conclusively found. That hasn't stopped scientists from exploring hybrid explanations. Perhaps the cold spot isn't caused by a single defect but by a cluster of them, their combined influence amplifying the effect. Or maybe defects interact with other phenomena, like supervoids, vast, empty regions of space where matter is unusually sparse. A supervoid aligned with a cosmic texture might magnify the temperature drop, creating a cold spot deeper and wider than either could produce alone. Ultimately, the debate isn't just about explaining one anomaly, it's about understanding the universe's structure on the grandest scales. Whether the culprit is a cosmic defect, a multiverse collision, or something entirely unforeseen, each theory pushes us closer to unraveling the cosmos' deepest mysteries. And until we know for sure, the cold spot remains a cosmic Rorschach test, revealing as much about our theories as it does about the universe itself. Dark matter and dark energy, the universe's most elusive ingredients, might be more than just cosmic placeholders. What if they're the lingering echoes of a cataclysmic collision between universes? These mysterious forces make up over 95% of everything in existence, yet we've never directly observed them. They don't emit light, reflect it, or interact with normal matter in any way we can easily detect. But their gravitational fingerprints are everywhere, shaping galaxies, bending light, and even accelerating the expansion of the cosmos. So why do they exist? One radical possibility is that they're artifacts from a time when our universe wasn't alone. Imagine two universes smashing together like waves in an ocean. The energy of that impact wouldn't just vanish, it could seep into the fabric of space-time itself, condensing into an invisible scaffold that holds galaxies together. That's dark matter. Astrophysicists have long puzzled over why galaxies rotate faster than they should, given the visible mass they contain. The answer: an unseen gravitational glue, dark matter binding them together. But where did it come from? If another universe once grazed ours, its gravitational influence might have left behind this shadowy residue, a kind of cosmic dust settling in the cracks of reality. Dark energy, on the other hand, is even stranger. Unlike dark matter, which clumps around galaxies, dark energy appears to be evenly spread throughout space, pushing the universe apart at an ever-increasing rate. Some theories suggest this relentless expansion could be the aftermath of a collision, like stretching a rubber band after it's been snapped. When branes or bubble universes collide, the energy released might not just create a new universe, it could also imbue it with a repulsive force, a kind of anti-gravity that lingers long after the impact. There's a compelling symmetry to this idea. Just as the Big Bang unleashed energy that formed stars and planets, a multiverse collision could have unleashed dark energy, shaping the universe's expansion in ways we're still deciphering. Even the timing fits. Dark energy only began dominating the cosmos's evolution a few billion years ago. Before that, gravity was winning, pulling matter together. Then something flipped. Could that something have been the delayed effect of an ancient collision, like a slow-burning fuse finally reaching its payload? Not all scientists buy into this explanation. Some argue dark matter could be primordial leftover particles from the Big Bang that never quite integrated into the visible universe. Others propose dark energy is simply a property of empty space, a cosmological constant baked into the laws of physics. But the collision theory offers a tantalizing alternative. What if these phenomena aren't fundamental at all? What if they're cosmic scars, the bruises and lingering tremors from a time when our universe wasn't floating in isolation, but locked in a violent embrace with another? The search for answers is far from over. Experiments like the Large Hadron Collider are hunting for hypothetical dark matter particles, while telescopes map the universe's expansion with unprecedented precision. Every anomaly, every deviation from expectation could be a clue. And if we ever find proof that dark matter or energy bear the fingerprints of a multiverse collision, it would rewrite not just cosmology, but our very understanding of existence. The universe's greatest mysteries might not be unsolved. They might just be waiting for us to look beyond our own cosmic horizon. The hunt for evidence of universe collisions isn't just theoretical, it's a race against time and technology, with scientists building next-generation tools to peer deeper into the cosmos than ever before. At the forefront of this effort are projects like the Simons Observatory, a state-of-the-art array of telescopes perched high in Chile's Atacama Desert. Designed to map the cosmic microwave background with unprecedented precision, it could spot subtle patterns like concentric ripples or elongated cold spots that might betray the gravitational tug of a neighboring universe. The key lies in polarization, the way light waves align as they travel through space. A collision could twist this alignment in specific ways, leaving behind a faint but telltale swirl in the data, like a fingerprint smudged on the edge of the observable universe. Meanwhile, the European Space Agency's Euclid mission is taking a different approach. Launching in the coming years, this space telescope will create a 3D map of billions of galaxies, tracing their distribution and motion across cosmic history. If dark flow, that mysterious drift of galaxy clusters, truly stems from a multiverse collision, Euclid's ultra-precise measurements might reveal its source, pinpointing the direction of the pull like a cosmic compass needle. The mission could also uncover bizarre voids or filamentary structures in the large-scale universe, anomalies that align with predictions of brane collisions or bubble universe mergers. But perhaps the most tantalizing tools are gravitational wave observatories. While current detectors like LIGO focus on ripples from black holes and neutron stars, future upgrades, and projects like the space-based LISA laser interferometer space antenna will tune into lower frequencies. These could catch primordial gravitational waves, vibrations from the universe's infancy that might carry echoes of a collision. Imagine listening to the aftershocks of a cosmic car crash billions of years later. Some theories even predict unique, burst signatures, sudden, asymmetric waves unlike anything produced by known astrophysical events. Then there's CMB S4, the next leap in cosmic microwave background studies. With detectors 10 times more sensitive than current instruments, it could analyze the cold spot in finer detail, searching for nested temperature variations or polarization patterns that defy conventional explanations. It might also detect textures, those hypothetical space-time kinks that could mimic collision scars. The challenge is separating noise from signal, like trying to hear a whisper in a hurricane. But with enough data, statistical anomalies become harder to dismiss as coincidence. Quantum physics is joining the hunt too. Labs are refining experiments to test whether entanglement, the spooky link between particles, could hint at higher dimensional leaks between universes. By entangling particles across increasingly vast distances and monitoring for anomalous correlations, researchers might uncover deviations that suggest interference from beyond our spacetime. It's a long shot, but in a field this speculative, every avenue matters. The stakes couldn't be higher. If any of these projects find evidence of a collision, it wouldn't just confirm the multiverse, it would rewrite the story of our universe's birth, evolution, and ultimate fate. And if they find nothing that's equally profound, it might mean we're alone in the cosmos after all, or that the multiverse's secrets are hidden even deeper than we dreamed. Either way, the search itself is expanding the boundaries of human knowledge, one experiment at a time. If our universe is just one among countless others in a chaotic multiverse, where collisions shape realities like waves crashing in a dark ocean, what does that mean for us? For humanity's place in existence, the philosophical weight of this idea is staggering. It doesn't just challenge our understanding of physics, it forces us to confront the very nature of meaning, identity, and purpose. Imagine standing on a shore, realizing the ocean you've mapped is just a droplet in an endless sea. That's the scale of the existential shift we're facing. Consider the concept of uniqueness. For centuries, we've clung to the idea that our universe, our planet, our species might be singular, special. But if collisions between universes are possible, even common, that cherished uniqueness evaporates. There could be infinite versions of Earth, infinite versions of you, each shaped by slightly different physical laws or historical twists. The thought is equal parts humbling and exhilarating. It's not just that we're not the center of the cosmos, we might not even be the center of our own story. Then there's the question of destiny. If universes collide, merge, and rebirth in an endless cycle, does anything we do truly matter? On one hand, it could feel nihilistic, our struggles, our achievements, even our civilizations might be fleeting flashes in an infinite cosmic storm. But flip the perspective and it becomes liberating. If existence is boundless, then every choice, every act of creativity or compassion ripples through the multiverse in ways we can't imagine. You're not just living a life, you're contributing to a tapestry of realities far beyond your own. The ethical implications are just as profound. If other universes harbor life, do we have a moral responsibility to them? Could a collision inadvertently wipe out entire civilizations, or more chillingly, might some civilizations engineer collisions to reshape reality to their will? These aren't just plot twists from a sci-fi novel. They're urgent questions if we accept that our universe isn't an island. The golden rule might need a cosmic update. Do unto other universes as you would have them do unto you. And what about the search for truth? Science is built on the belief that the universe operates by consistent, discoverable laws. But if those laws change every time universes collide, can we ever find permanent answers? Some philosophers argue this doesn't undermine science, it expands it. Instead of seeking a single theory of everything, we might need a menu of theories, each valid in its own cosmic context. The pursuit of knowledge becomes less about uncovering fixed rules and more about mapping infinite possibilities. Perhaps the most haunting question is one of connection. If we're the products of a multiverse shaped by collisions we'll never fully understand, are we ever truly alone? Could fragments of other realities linger in ours like echoes in a canyon? Some spiritual traditions have long hinted at this ideas of parallel realms, unseen dimensions, or cyclical existence. Modern physics might be catching up to ancient intuition, blending the empirical with the metaphysical in ways that redefine both. Ultimately, the collision theory doesn't just change how we see the cosmos, it changes how we see ourselves. Whether it's a humbling dose of cosmic insignificance or an invitation to dance in an infinite multiverse, one thing's certain: the universe or universes are far stranger, grander, and more interconnected than we ever dared to dream. And in that vastness, there's a peculiar comfort. However chaotic the multiverse may be, we're here now asking these questions, and that alone is a miracle worth marveling at. What if the collision between universes didn't just reshape space but time itself? Strange temporal phenomena, from déjà vu to unexplained time loops, might not just be tricks of the mind. They could be echoes reverberating from a cosmic crash, ripples in the fabric of reality where past, present, and future blur. Picture a bell struck so hard, its vibrations never fully fade. Now imagine that bell is space-time, and the clapper was another universe slamming into ours. The resulting distortions could twist time into knots, creating pockets where the normal rules no longer apply. Take the infamous WOW signal, a mysterious radio burst detected in 1977 that lasted 72 seconds, never repeated, and defies explanation to this day. Could it have been a fragment of another universe's timeline bleeding into ours, a fleeting moment when two realities briefly synced? Or consider the bizarre case of the Tord Man, an urban legend about a traveler who arrived at a Tokyo airport in the 1950s, insisting he was from a country that didn't exist, complete with a passport and currency. When officials detained him overnight, he vanished from a locked room. Skeptics dismiss it as a hoax, but what if it was a temporal glitch, a crack in reality where two versions of Earth momentarily overlapped? Physics isn't silent on these possibilities. Einstein's general relativity allows for closed time-like curves, paths through space-time that loop back on themselves, effectively creating time loops. Under extreme conditions like the gravitational chaos of a universe collision, these curves could form naturally. Imagine two branes grazing each other, their gravitational fields twisting space-time like a spiral staircase. If you walked far enough in one direction, you might return to your starting point, not just in space, but in time. It's a concept straight out of Interstellar's Gargantua, but with a multiverse twist. The black hole isn't the time-warping engine, the collision is. Even quantum mechanics offers clues. Particles entangled across space mysteriously influence each other instantly, but what if they're also entangled across time? Experiments have shown particles behaving as if they're reacting to future measurements before they happen, a phenomenon called retrocausality. Now scale that up. If entire regions of spacetime became entangled during a collision, could events in our past be shaped by futures we haven't lived yet? It's as if the universe keeps stuttering, replaying fragments of a cosmic film strip where the reels got tangled. Then there's the eerie consistency of historical time loops, events like the Groundhog Day effect, where people report reliving moments with unsettling precision. Most write these off as neurological quirks, but could they be localized fractures in space-time, weak spots where the boundary between universes is thin? In regions where collisions left spacetime warped, time might not flow linearly but in pulses or spirals, repeating like a scratched record until the groove rights itself. The implications are dizzying. If collisions can bend time, then our perception of history as fixed and linear might be an illusion. Ancient myths of cyclical time, like the Hindu concept of yugas or Nietzsche's eternal recurrence, could reflect an intuitive grasp of a deeper truth. Even modern physics entertains the idea of a block universe where past, present, and future exist simultaneously, and our sense of time's arrow is just the way we experience the slice of reality we're in. A collision could jostle that block, making adjacent slices briefly visible. Critics argue this is all speculative, and they're right. Without direct evidence, these ideas linger at the edge of science fiction. But remember, black holes, gravitational waves, and the Big Bang itself were once dismissed as mathematical fantasies. The key is in the anomalies, when astronomers detect stars that seem older than the universe, or when particle physicists find data that defies causality. These aren't just errors, they're invitations to look deeper. Perhaps the most haunting possibility isn't that time loops exist, but that we're inside one. If our universe was born from a collision, could its death and rebirth be part of an infinite cycle? Every galaxy, every planet, every life playing out again and again, with slight variations each time. It's a cosmic haunting where the ghost isn't a spirit, but time itself, echoing endlessly through the multiverse. Whether these echoes are real or not, the search for them reminds us. Time may be the most mysterious dimension of all, and the next great frontier in understanding where universes collide. What if we're not the only civilization to have pondered the cosmos? What if, in the unfathomable vastness of the multiverse, another universe once teemed with intelligence, and when it collided with ours, fragments of their existence bled into our reality? The idea might sound like pure fantasy, but consider this. If universes can collide, and if life can emerge under the right conditions, then the echoes of another civilization might be hidden in plain sight, woven into the fabric of our own history. Think about ancient myths that span cultures separated by oceans and millennia, floods that purge the world, gods descending from the sky, or advanced beings imparting forbidden knowledge. The Babylonian epic of Gilgamesh, the biblical story of Noah, and the Mayan Popol Vuh all share eerily similar tales of cataclysmic floods and divine intervention. Could these stories be more than coincidence? Might they be distorted memories of a collision, a moment when realities touched and the inhabitants of another universe left their mark on ours? Even the sudden explosion of human creativity 50,000 years ago, known as the Great Leap Forward, has puzzled anthropologists. Was it just evolution, or could an outside influence have accelerated our development? Then there's the enigma of unexplained ancient technology. The Antikythera mechanism, a 2,000-year-old Greek device for predicting astronomical positions, exhibits engineering sophistication that seems out of place in its time. The Baghdad battery, a clay jar thought to generate electricity, hints at knowledge we didn't expect from antiquity, and the precision of the pyramids of Giza continues to defy straightforward explanations. While mainstream archaeology attributes these to human ingenuity, what if they're the result of borrowed ideas, artifacts influenced by contact with a civilization from a universe with different physical laws or advanced understanding? The cosmic collision theory could also shed light on the Fermi paradox, the unsettling silence of the universe despite the high probability of alien life. If intelligent civilizations are common, why haven't we detected any? Perhaps because they're not out there in our universe, they're elsewhere, in parallel realities that occasionally brush against ours. Their signals, their probes, even their colonies might exist just beyond the dimensional veil, detectable only in fleeting anomalies. If we're searching for radio waves when we should be searching for gravitational ripples or quantum echoes, we might be looking in entirely the wrong place. Now imagine the darkest twist. What if a collision wasn't just a passive transfer of knowledge, but an extinction event? If another universe's physics were hostile to ours, say, with stronger nuclear forces or a different speed of light, its mere proximity could have triggered catastrophic changes. The mysterious Younger Dryas period, around 12,000 years ago, saw sudden climate shifts and mass extinctions that science still struggles to explain fully. Could a collision have momentarily destabilized Earth's environment, wiping out advanced cultures and leaving only scattered survivors to pass down garbled warnings in myth and legend? This isn't just about ancient aliens or sci-fi speculation. Modern science entertains the possibility of quantum archaeology, the idea that if parallel realities interact, their histories might subtly influence one another. Future experiments could search for statistical anomalies in historical events, patterns too unlikely to arise by chance, as potential evidence of cross-universe interference. Even our dreams, those strange narratives that feel so vivid yet slip away upon waking, might be glimpses into other versions of reality where we exist with different lives, different choices. Of course, skeptics demand tangible proof, and rightly so. But if civilizations from colliding universes left traces, where would we even look? Some physicists suggest scanning the cosmic microwave background for unnatural patterns, mathematical constants encoded in the radiation, or asymmetries that resemble artificial structures. Others propose digging deeper into quantum noise, the static of empty space, for signs of organized information leaking through from another reality. It's like tuning a radio between stations and catching a fragment of a broadcast in an unknown language, faint, incomprehensible, but undeniably there. The most profound question isn't whether parallel civilizations exist, it's what their existence would mean for us. If we're not alone in the multiverse, but surrounded by countless iterations of intelligence, each shaped by their own cosmic accidents, then humanity is both insignificant and extraordinary. Insignificant because we're one thread in an infinite tapestry. Extraordinary because we're here at all, able to ask these questions, to reach across the dimensions with our minds, if not yet our hands. The universe or universes may be far stranger than we ever imagined, but the greatest mystery of all is that we're here to unravel it. Imagine two universes drifting toward each other in the vast multiverse. One a sprawling cosmos with galaxies, stars, and planets. The other a twisted realm where gravity is 10 times stronger and atoms can't hold together. When they collide, one might shatter like glass while the other barely flinches. Why? The answer lies in the delicate balance of physical laws, a cosmic game of survival where the rules are written in the fabric of reality itself. Some universes are built to last. Ours, for instance, strikes a rare equilibrium. Gravity is just weak enough to allow galaxies to form without instantly collapsing. Nuclear forces bind atoms tightly but not too tightly, and dark energy's gentle push keeps space expanding without tearing everything apart. These Goldilocks conditions aren't just lucky, they're the result of a brutal multiverse filter. In the chaos of collisions, universes with unstable physics, where constants are slightly off, where matter decays too quickly or forces don't balance, are weeded out. They flare into existence and vanish like bubbles popping in a boiling pot. Only the robust ones, the ones that can withstand shocks and adapt, endure long enough to nurture complexity, let alone life. But what makes a universe robust? One theory points to redundancy. Think of our universe's structure like a spider web. If one thread snaps, the others hold firm. Dark matter's gravitational scaffolding keeps galaxies intact even when spacetime is warped. Quantum fields stabilize matter against fluctuations. Even if another universe grazed ours, these failsafes might absorb the shock, preventing total collapse. Compare that to a hypothetical universe where electromagnetism is slightly stronger. Stars would burn out in millennia, leaving no time for planets, let alone life, to emerge. Collisions would be apocalyptic for such fragile realities. Another factor is symmetry. Our universe is filled with invisible symmetries, laws that stay constant no matter where or when you look. These symmetries act as shock absorbers during collisions. When branes or bubble universes smash together, the energy released can scramble physics, but symmetries resist that chaos. They're like the keel of a ship, keeping reality upright in a storm. Break those symmetries, though, and a universe becomes vulnerable. Imagine a reality where the strength of gravity varies randomly from place to place. A collision could rupture it like a pane of glass with no internal support. Then there's the dark horse of survival, entropy. In most universes, entropy, the trend toward disorder, rises inexorably, leading to heat death. But some theoretical models suggest collisions can reset entropy, like shaking a snow globe. If a universe is caught in a cycle of collisions, each crash might recycle its energy, staving off decay. Our cosmos isn't cyclical as far as we know, but others could be locked in an eternal dance of destruction and rebirth, their longevity owed to the very collisions that would spell doom for lesser realities. The eerie implication: if our universe has survived this long, it might not be an accident. It could mean we're living in a multiverse sweet spot, where the physics is just stable enough to endure. Or more unsettlingly, it could mean we're in a universe that's already been reshaped by past collisions, its laws fine-tuned by catastrophe. The scars might be hidden in the cosmic microwave background, or in the way galaxies spin, subtle clues that our reality is a survivor of something far more violent. This isn't just about cosmology, it's about stakes. If collisions are common, then our universe's survival isn't guaranteed. A future impact could rewrite physics, unraveling the constants that let stars shine and life exist. Or if we're lucky, it might leave us untouched, a testament to the resilience of a universe built to last. Either way, the message is clear. In the multiverse, longevity isn't an accident. It's a badge of cosmic toughness, and our universe might just be a reigning champion. If another universe comes barreling toward ours like a cosmic freight train, should we be prepping survival kits or just enjoying the ride? The idea might sound absurd. How do you even prepare for something that could rewrite the laws of physics? But let's entertain the thought for a moment. First, the good news. If a collision happened before, say, triggering our Big Bang, we wouldn't just survive it, we'd owe our existence to it. The bad news: a repeat performance might not be as kind. Picture two soap bubbles merging gently versus two cinder blocks smashing together at light speed. The outcome depends entirely on the physics of the other universe. If it's a gentle collision, branches of the multiverse barely grazing each other, we might not notice anything beyond some weird gravitational ripples or stars flickering oddly in the sky. Astronomers would have a field day studying space-time glitches, while the rest of us scroll past headlines like "Scientists detect universe-sized dent in reality" between coffee sips. But if it's a head-on smash with a universe where, say, protons are unstable or time runs backward, that's when things get dicey. Matter could unravel without warning. Black holes might pop into existence like cosmic landmines, or worse. We could wake up in a reality where pizza is considered a health food. Okay, maybe not the worst outcome. Now, the million-dollar question: is there anything we could actually do? Stockpiling canned goods won't help if atoms start misbehaving, and building a bunker won't shield you from a sudden reversal of entropy. But here's a wild thought. If collisions leave detectable patterns like those gravitational waves or cold spots, maybe we could invent an early warning system. Imagine a universe weather forecast predicting dimensional storms centuries in advance, giving civilizations time to, well, panic gracefully. Alternatively, if string theory's right and we're floating on a brane, could we someday steer away from collisions? It's the ultimate defensive driving fantasy, navigating the multiverse highway with cosmic GPS. Of course, all this assumes we'd even recognize a collision in progress. What if the signs are subtler? A sudden shift in fundamental constants might first show up as lab equipment glitching, scales refusing to balance, particles behaving erratically. Or maybe déjà vu would spike as timelines fray, with people swearing they've lived this moment before. Philosophers might argue we're already in a post-collision universe, and that's why quantum mechanics feels so bizarre. The truth is, we're like ants on a railroad track, theorizing about locomotives we can't see or comprehend. But here's the cosmic punchline. If another universe is on a collision course, worrying about it is like stressing over tomorrow's sunrise. It's either inevitable or irrelevant, and either way, we're along for the ride. So maybe the best prep is to keep staring at the stars, laughing at the absurdity of it all, and appreciating the strange, fragile reality we've got while it lasts. From cosmic soap bubbles crashing in higher dimensions to black holes hiding portals to other realities, we've journeyed through some of the wildest ideas in modern physics. The possibility that our universe once collided with another, or even owes its existence to such a collision, isn't just science fiction. It's a frontier where cutting-edge math meets the deepest mysteries of existence. Think about it, the cold spot in the cosmic microwave background, the eerie pull of dark flow, the quantum whispers of entanglement. Each one could be a breadcrumb leading us to proof that we're not alone in the multiverse. But here's the thing, we're standing at the edge of discovery, peering into the unknown. The theories we've unpacked today, from brane collisions to cyclical universes, aren't just stories. They're testable hypotheses, fueled by anomalies that refuse to fit neatly into our textbooks. And that's what makes this so exhilarating. Every unexplained ripple in space-time, every strange pattern in ancient light, could be the clue that changes everything. So now it's your turn. What do you think happened? Was the Big Bang the aftermath of a cosmic fender bender? Could the cold spot really be the bruised aftermath of another universe bumping into ours? Or is there something even stranger lurking in the data, waiting for its moment to rewrite reality as we know it? Drop your boldest theories in the comments. Let's keep this cosmic conversation rolling. Because in a multiverse of infinite possibilities, the wildest idea might just be the one we haven't thought of yet. Stay curious, keep questioning, and remember, the universe or universes are always stranger than we imagine.